Okay, well, let me answer that. Take one topic at a time. Um,
Sure.
you have not ever, to my knowledge, in anything I've seen of yours, explained where matter came from, where space come from, or where time came from. You're concerned about these stars being a certain distance away, but I think if you, I think you would agree that there is an enormous amount of mass in the universe. If you collected all the stars together and squeezed them into a ball, and all the planets that we've seen, there'd be an enormous amount of material. Where did that come from?
You wouldn't have material actually. The temperature would be so high that it would all basically be radiation.
Okay.
It would just be pure energy.
Okay, so where did the
And this
energy come from?
actually this actually counts as evidence
So where did the energy come
in
from?
favor of the Big Bang theory.
Yeah,
Hello? Sorry?
time, space, matter, energy. Where did they come from? To say
That I
something,
don't
you say something exploded with the
that I
Big
don't
Bang.
have
What exploded?
that I don't have an answer to. That being said, though, that's irrelevant to the question of how old the universe actually is. Why the universe went from its initial state of a very hot, very small, and very dense state into the current cool and sparse state, we don't know yet. The question is how much time elapsed between these two states, and the answer is closer to 13.8 billion years than it is to 6,000.
And how do you know that since you're 24 years old? How do you know there's 13.7 billion years? You're basing that on a distance to the stars? Why that number 13.7?
But no, as I say, it's the Friedmann equations and the observation of the cosmic microwave background radiation.
Okay, explain these equations. People watching this debate are not impressed with all your use of huge words. I have a dictionary too. I could look up a bunch of big words. Explain it in layman language for the average listener. What does this equation tell us, and where did it come from, and what's the point?
Well, I'm using the big words, Kent. Friedmann is two syllables. If you want me to start showing off, I'll turn on my webcam and start doing tensor calculus. This is just me trying to explain it at the most basic level.
Okay, what is the Friedmann equation? What is the Friedmann equation?
The Friedmann equations, as I mentioned last time, are derived from Einstein's field equations in general relativity.
Which still doesn't tell us what it is.
Sorry?
That still doesn't tell us what it is.
Well, I'll tell you if you let me.
Yes, please do.
Okay, so the Friedmann equation tells us how the space and how the universe changes based on the energy density of different parameters. How much mass is there, how much radiation is in the universe, what the relative concentrations of these things are, and how the universe can be expected to change in its shape and its size based on these parameters.
Okay, let's take that one bite at a time here now. Are you saying the universe changes its shape and behavior? What exactly is the shape of the universe, and what is beyond that shape?
Not its behavior so much, it's
okay.
shape and whether it expands or contracts.
So what is beyond the edge of this expanding and contracting universe that you envision? What is beyond the edge?
It's not clear as to whether there's an edge or not. There is an observational edge, and this lies at the cosmic horizon. But beyond that, there's nothing that we can say by definition, since that falls outside of the observable universe. I can only speak with confidence about what's inside of the observable universe.
Okay, so this Friedmann equation tells us that if we have increased energy or increased mass, the shape of the universe changes. What on earth does that have to do with anything you're talking about here?
Well, when you take into account the distribution of different parameters, things like the amount of radiation, things like the amount of mass, and you get this by the way of an examination of the cosmic microwave background radiation. Once you have these parameters and you plug them into the equation, you can determine to what extent the universe has been expanding, and you're able to derive from this equation the age of the universe. If you know how quickly it's expanding, and you know how the distributions have been changing over time, then it's very trivial to calculate how old the universe is.
Okay, now
very simplified.
Hang on, my 8-year-old grandson is watching this. You're saying that some equation tells us that if we add more energy, the distribution of the material, the mass of the universe changes. That's like, duh. If you drop a hand grenade in a room, the distribution of the material changes by adding energy. That's still not proving any age.
That's not what I said. I said that the different parameters, like things like the amount of radiation versus the amount of mass.
Okay. So if the amount of radiation changes by adding energy, so what?
You don't add energy. You transfer between different types of energy.
Okay, yeah, there's different types of energy. I agree.
Yeah.
But the point is,
if you convert between these different types of energy, then if you do it to a sufficient extent, then the behavior of the universe is going to change. If you have more of this, the universe will expand. If you have more of that, the universe will contract, and so on. And the Friedmann equation tells us how exactly this works and how quickly these things are changing.
That's wonderful. If you add energy, things expand. You can add energy to a room and the air expands. Ask any weatherman; they understand that very
Not
well.
necessarily. No. You can. There are ways of adding energy and making things contract. If, for example, you were to have a lot of this energy, some of the pure energy coalesced into mass, it reaches the threshold energy to generate mass, and the mass has a gravitational pull, then things start to contract rather than expand.
Oh, wait.
You need to understand how these various. You have to understand how these various parameters.
Okay. Let me see if I understand what you said. You're saying that energy can be turned into matter. Is that what I heard you say? And where has this been demonstrated? Just energy. Let's take all the heat energy you want. What matter is that going to produce?
Are you familiar with the equation E equals mc squared?
I am indeed.
Okay, then it should be trivial as to how this happens. The process can go in both directions. You can.
Okay, I'm asking you, where has it been observed? Energy equals mass times the speed of light squared, which is what C stands for. That was Einstein's idea. And it may certainly be true, but you're saying that goes both ways? If it does, if the energy can be turned to mass, where has this ever been demonstrated? I think mass can be turned to energy all the time. You can burn up a wood pile and get a lot of heat out of it and reduce the mass to energy, but where can you get the energy to turn into mass? I'd like an example of that, please.
The wood pile thing is not an example of E equals mc squared. That's a chemical reaction.
Okay, but it's an example of mass being turned to energy. I would like you to show me or tell the audience, where has energy, just energy, ever been turned into material, mass, something solid?
Inside of particle accelerators, you can get masses very small masses, and the sum of those masses was, let's say, less than x. And you get these masses going very quickly. You add energy to them without actually, changing the mass state. They still have a constant rest mass.
Think what you're saying. You take. Okay.
Hold on. You take these two masses, and their total mass is less than x. And you speed them up and you crash them together, and then the end result is a mass that's greater than x. And you get this because of the energy that you've added to them as a result of them speeding up.
So the energy, your contention is you speed up two particles, crash them into each other. The result weighs more than the initial two particles. You started with two particles. What if you start with nothing, just energy?
If you start with just energy,
you can't have your two particles. You can't have your two particles. Just energy, turn it to mass. Where has this ever been done?
The Casimir effect is one good example.
Explain that to the average audience.
Well, for the average audience. Well, you have a vacuum, and the vacuum has a ground state. That's the minimum amount of energy that any system can have. And this ground state, it basically has a certain amount of energy. And from this minimum amount of energy, you have particles and antiparticles popping in and out of existence. And this has been demonstrated with experiments like the Casimir effect, where you have the result of this vacuum energy causing two plates that are close enough to each other in order to be affected by this ground state, clamping shut together in accordance with predictions, and without anybody actually adding any energy to it. It's a consequence of these virtual particles.
Okay, are these two plates that are clamping together, are they made of material? Are they visible?
Yes.
So you're starting with material. I would like you to have nothing to start with except energy.
There's nothing between them. That's the point. There's nothing between these plates. And this supposedly nothing causes something to happen. The plates end up clamping together.
Other than just a vacuum or a magnetic reaction or a...
there's just a vacuum there. There's nothing else.
Okay, so we know that magnetism, which we cannot see, will cause two magnets to clamp together. I know, but we know that a vacuum between two objects will cause them to clamp together. So you're saying there is something else.
The vacuum has a certain ground state, as I said. And
so
I don't remember the exact details of how the experiment goes, but as a result of these virtual particles, the plates do end up clamping together.
And do you think an example like that is enough to put your trust in that the whole universe, everything we see with trillions of tons of material, was created out of nothing in that manner?
When did I say that it was, Ken?
What now?
When did I say that? Sorry?
Well, I was asking you, where did the material in the universe come from? And you give an example of this Friedmann equation and matter popping in and out of existence. Is that satisfy you that the whole
No,
universe
Ken,
came
that's
to
not how
being
this
this way?
Ken, hold on. The way this conversation went was you asked me to demonstrate how old the universe was. I went into a conversation about the Friedmann equation. We started talking about the composition of the universe via things like energy and mass. And then we got to Einstein's equation, and you asked for an example of how energy can be turned into mass, which is what I just gave.
So
at no point was this. At no point was what I just told you a premise for an argument of the universe coming from nothing. There are some models that do suggest this may be the case, but nobody's saying that this is something that's as firmly confirmed as the Big Bang theory. So let's not equivocate here, Ken.
I'm not equivocating. I'm trying to draw it out of you that you have an intense religion, not a science. Nobody's ever seen any of the universe pop into or out of existence, or without incredible energy input to create this energy vacuum or whatever you called it that caused the two plates to clamp together. This was all done in some machine made by some man, I'm assuming, with some intelligence. This doesn't just happen by itself. So back to my original question.
That's not the point. Ken, you're missing the point.
No, I think I've got the point really well.
Hold on, you're equivocating between what I'm trying to demonstrate and what you want me to try to demonstrate. What I'm demonstrating is that energy can be turned into mass. That's what you asked me to demonstrate. Now you're saying, aha, but you haven't demonstrated that the universe can't come from nothing.
Okay, well,
I mean, if you want to do that, by all means, try it. But like, you're arguing with yourself now.
So you're saying that an experiment was done in obviously some man-made machine using a lot of energy, a particle accelerator, which takes an enormous amount of energy. Ask the folks in Europe.
This case, no. For the effect, no.
Okay. Was there any kind of design to this particle accelerator, or did it come by chance? Did somebody design it?
Well, clearly, yeah.
Okay, good. So if particles can come in and out of existence, let's assume that's true. I think I'd have to watch that to have mass change to, energy change to mass. I think we see mass change to energy all the time, and we see all the stars are burning up. Our sun is burning up. It's changing mass to energy. But is there any place where the sun's energy can be turned back to mass material?
That's not. It could be, but that's not part of the process. Nuclear fusion just says that. Well, let me think about that for a second. It could be the case that you have two lighter elements that are fusing into something that is less than the sum of their masses. In which case, some of that mass is lost to energy.
I agree. The mass turns to energy. You're missing it.
Okay, but you have to understand the equal sign points in both directions. Now, whether or not this happens in the sun, I don't remember at the moment. But I do know that, at least in the case of the Casimir effect and other similar experiments testing quantum vacuum fluctuations, this is all part of quantum field theory.
Sure, and it's a theory.
It's possible for energy to turn into mass.
It's a theory. I'm asking, where has this been observed? Einstein says
the Casimir effect.
Well, could it be the equation, the equal sign should not go both directions? It's only observed going one direction.
Come on, Cass. An equal sign is commutative.
Oh, believe me, I understand. I taught math for years. I think I can handle an equal sign, but I'm asking you, I know mass can be turned to energy, but you would like the audience to believe, I assume you would like the whole world to believe this evolution theory, which really would have everything come into existence from nothing. Ultimately, you have to start with nothing and have some kind of material. Where's the material and the energy? You got either one or the other. You got to start with one or the other or both. Where did it come from?
I told you already, we don't know where it came from, but that's not what the Big Bang tells us. The Big Bang tells us how the universe came from its initial very hot and very dense state, where there was a lot of energy, into the current very sparse and very cool state. Okay,
so would I be safe to say that you do not know where the initial energy came from to heat up this speck or whatever? You're saying you don't know where the energy came from. Okay. And this energy...
Yeah, nobody knows.
Nobody knows. Okay. The energy, we have a thunderstorm here. We may lose power. I don't know.